Okay, so we will continue talking about the Pontryagin-Thom construction. Last time I was in a bit of a hurry at the end, so I will recall some of the constructions and do them a little bit more slowly. So let's recall. So we had Q0 and Q1. These were compact oriented submanifolds without boundary. And we defined a cobordism, what a cobordism was. So a cobordism from Q0 to Q1. So in the oriented world, cobordisms have directions. So cobordism from Q0 to Q1 is an oriented compact manifold W, a submanifold of the product of 0, 1 with X with boundary. And I'm going to do a slightly stronger definition than last time. I'm going to require that near 0 times X, so the intersection of W with 0 epsilon times X is equal to 0 epsilon times Q0. And the same thing near 1. 1 minus epsilon. Epsilon times X is equal to 1 minus epsilon times Q1. So I'm going to require that. So that implies, that the boundary of W is 1 times Q1 minus 0 times Q0. Okay, so this is not a very strong implication, but sometimes, sometimes people define cobordisms as a manifold that just has this property here and that is transverse to the boundary. So sometimes we only, or sometimes it is only required that star holds and that W is transverse to the boundary of 0, 1 times X. So this is just a small subtlety. So every time you have such a cobordism that satisfies this, then you can actually deform it, homotope it to a cobordism that satisfies a stronger condition. Okay, so if I don't know, if I have my cobordism something like this, I can always homotope it so that it actually is kind of constant in small neighborhoods. Like that. And that's just because of transversality. Okay, so this is an exercise if you want. Like if you only require the second condition so that the boundary is this and that it's transverse to 0, 1, the boundary of 0, 1 times X, then you can find another cobordism that satisfies this condition, this stronger condition here. The reason I am imposing this is because I want to talk about normal bundles and just to make things a little simpler. So now I'm going to tell you how to think about the normal bundle of W. So to do that, I'm thinking about normal bundles using Riemannian metrics to make things simpler. So let's fix a Riemannian metric G, Riemannian metric on X. So that will induce a Riemannian metric on the product with 0, 1. So this is just going to be dt plus G. This is a Riemannian metric. On 0, 1 times X. So it just means, if I have a tangent vector on 0, 1 times X, I basically will have a multiple of dd theta, ddt, and then I'm going to have a vector in X. And the inner product is just, you take the inner product on R, so it's just the multiplication, and then you take the inner product on X. So in particular, the direction ddt is orthogonal to the tangent space of t times X. Okay, so basically these slices here, this is orthogonal to the direction ddt. Okay, so if you use this condition, if you use this fact near 0 or near 1, what you obtain is that basically the normal bundle to W is going to be the same or very isomorphic in an obvious way to the normal bundle of Q0 near 0 and to the normal bundle of Q1 near 1. So how do let me just write this a little more precisely. So you can think of the diffeomorphism that takes the boundary of W to Q1, disjoint union Q0 with the opposite orientation. So let this be the natural orientation preserving orientation preserving diffeomorphism. Okay, so this just it's basically the diffeomorphism that takes 1 times Q1 to Q1 and 0 times Q0 to Q0. Okay, I just want to do this to say that if I can actually look at the normal bundle of Q1 as a bundle over as a bundle over this piece of the boundary of W. Okay, so and the notation is basically the pullback of the normal bundle of Q1. So this is a bundle over 1 times Q1. And because of this condition, because DDT is orthogonal, this is equal to the normal bundle of W restricted to 1 times Q1. And similarly, the pullback of the normal bundle of Q0, or I should say minus Q0, is equal to the normal bundle of W. Well, I guess when you say normal bundle, the orientation is not really very relevant. Well, let me still write it like this. Okay, so a framing on W is just a choice of a framing on the normal bundle, so a choice of a basis for the normal bundle at every point. So framing eta on W induces or restricts two framings on Q1 and negative Q0. Okay? So now, if Q0, eta 0, and Q1, eta 1 are framed submanifolds we say that a framed cobordism W eta from Q0 eta 0 to Q1 eta 1 is, well, let me write it like this. A framed cobordism from Q0 eta 0 Q1 eta 1 is a pair, is a framed compact manifold with a boundary such that, I guess you can write, W is a cobordism from Q0 to Q1. And when I restrict eta to Q1, I get eta 1. And when I restrict eta to minus Q0, I get eta 0. Okay? That's what a framed cobordism is. A comment here is that if you don't want to bother, if you for some reason you don't like this condition here, that it's that cobordism is horizontal, is kind of constant near 0, near 1, you don't really need it. You just need it to be transverse. But then you have to say a little more. You have to say, well, the normal bundle isn't necessarily like the orthogonal complement of the tangent space, but it's just any kind of transverse direction. And you can say, well, this transverse direction to W is going to be canonically identified to the transverse direction to Q0, near 0, and to the transverse direction to Q1, near 1. So, but if you impose this condition and you fix the Riemannian metric like this, that makes it's kind of easier to see that if you are in the kernel of the tangent space to W, then you cannot have any DDT components. You have to be completely contained in the tangent space to X. And therefore, you have to be equal to the normal bundle of Q0. Okay? Let me stop and take a break to see if there are any questions, if I can say things more slowly.
Where we can see this, in which book?
I think Milner has nice. Milner talks about this. The differential no, what is it? Topology from the differential viewpoint.
Okay.
Yeah.
Thanks.
Mm-hmm. Yeah, I mean, to read about cobordisms, I think Milner has another book called the H-cobordism theorem. And there he talks about cobordisms, but then I think that he doesn't really talk about framed cobordisms in that book. Okay, let's talk maybe, well, let me first post an exercise. I think I already wrote this last time, but it's just proving it's actually easier if you put that condition of being constant near 0 and near 1. So the exercise is that being framed cobordant is an equivalence relation. I mean, if you want, you could even put the condition of the framed cobordism that the framing is constant near 0. Because this identification with Q0, it doesn't only work at 0, but it works near 0. So you can also identify the framing, not just at the point 0, but near 0 here, and the same thing near 1. And that way you can just actually glue the two framings. But if you don't have that condition, then you could have like a point of non-smoothness, so you have to smoothen it a little bit, so it's slightly more complicated. But anyway, you can do that. So like, for the cobordisms, what I'm saying is like if you have, say, something coming like this and something going like this, then they don't necessarily glue to a smooth manifold. You might have to smoothen them if you just require the boundary to be the same. But if you could require them to be sort of equal to a cylindrical cobordism near that point that you're gluing, then you can just literally glue and it's going to be smooth. Okay. These kinds of exercises, that's when you really start to get your hands dirty with differential topology. So I encourage you to do that. And you see that the transversality theory is just kind of a technical theory that allows you to do everything that you would like to do, that the picture tells you should be able to do. Okay, so let's do some examples, and I'm gonna now do some things very concretely to try to get everybody on the same page. So the first example is has to do with degree theory. So let's say you have points, I don't know, P1, P2, and P3. Okay, this is my manifold Q0, and then my manifold Q1 is just a point Q. And the orientations are plus, plus, and minus. And here I have a plus. And these are all contained in X. So given the orientation, I also, I also get a framing. So these orientations like induce a framing. Yeah, because that's just the, you basically just choose the basis of X with a positive sign for P1, P2, and with a negative sign for P3. Okay, so the framings, X is oriented. The framing is just the orientation of X, or is induced. Because the normal bundle is everything. Is induced from the orientation of X. And what I'm going to do now is I'm going to construct a framed cobordism from Q0 to Q1. So I'm going to define two paths first. So let's gamma of t, gamma and eta. And I'm supposing that X is connected. Otherwise, I can't do this. So I'm going to define two paths. Smooth paths. So gamma of t, gamma is going to connect P1 to Q, and eta is going to connect P3 to P2. So actually, let me switch the signs. Let's say this is minus and this is plus. Okay, so gamma of t is going to be identically equal to P1 if t is between 0 and epsilon, and Q2, or in Q, if t is between 1 minus epsilon to 1. So, I mean, yeah, you can draw a picture of P1, P2, P3, and Q. This is gamma. And then eta will be identically equal to P2 if t is in 0 epsilon, and P3 if t is in 1 minus epsilon 1. Okay, so now I have to be, you have to be a little clever, because you want a path, sort of you want to do, I kind of did this last time already, but you want this path gamma to represent something like this, and you want the path eta to represent something like this. Okay, so I'm going to define gamma tilde and eta tilde that go from 0, 1, excuse me, to 0, 1 times x. And I mean, gamma tilde is just going to be the graph of gamma. So gamma tilde of t is just t and gamma of t. So it's just this path here. And then eta tilde is a path that has to kind of go a little bit and come back. So I'm going to define this to be t times 1 minus t, and then 8 of t. This is kind of the clever path that leaves here, actually goes all the way to 1/2 and then comes back. Okay? And now you can define your coordinatism to be just the images of the union of the two images. I mean, you can assume, to make things easier, for this really to be a submanifold, that these paths don't intersect. Okay, that these points are all different and these paths don't intersect. Okay, so this is just going to be the image of 0, 1 union the image of eta tilde. Okay, so then you can, it's easy to see because of the way that we that we define this, that what is the boundary of W? So the boundary of W is going to be, well, it's going to be Q times it's going to be 1Q union. Now I'm going to have all the points here. So this point's going to come with a minus sign. So it's going to be minus P1, no, minus 0 P1. Maybe let's just put comma. Then I have this was P2 and this was P3. Actually, I think I want the path going the other way. Yeah, from P3 to P2, because then I have minus P3 0, and then I have plus P2 0. No, the other way. I don't really like this eraser. I have to change it. Minus 0 P3 and then 0 P2. Okay, so you can check this, but basically what you get is you get 1 times Q1 minus 0 times Q0. And then as far as framings, that's kind of, for the gamma tilde, that's pretty easy to see the framing for this part here of W. Because here, the tangent space to W at a point, I don't know, Tx, this is canonically isomorphic to the space, to the tangent space. No, sorry, this is generated by ddt no, sorry, this is one-dimensional, and it's just generated by ddt plus gamma prime of t. So this is an equality. And then this is naturally isomorphic to the tangent space at x to x. No, sorry. The kernel of that, the orthogonal complement of that. Yeah, so the normal bundle at Tx of W, which is the same as the orthogonal complement. I don't like writing on this very much. This is naturally isomorphic to the tangent space at x. And the natural isomorphism, I mean, it is very natural. What you do is you take a vector here, and you just take it to v, and then the first coordinate you put g of gamma prime of t v with a minus sign. So you take the inner product of gamma prime of t and v with a minus sign d dt plus v. Okay, so kind of, if you take the inner product of this with this guy, that's going to be 0. And this is an isomorphism you can check. It's clearly injective, and the two spaces have the same dimension. Okay, so this is just to say that, you know, when you look at the picture, there is a canonical isomorphism for at each fiber for each t with the tangent space to x. So, you know, you can choose a fixed basis here, and that will give you a framing along W, and that's going, you know, if you can use that, for example, here and here, and that will coincide with the framings that you chose. I mean, I'm being a little sloppy because, like, to do this, you really have to fix just one. You really would like to fix one basis, and choosing an orientation is the same as choosing a basis up to isotopy. So, you know, the two are something that I kind of said. I think that the set of bases for Rn has two connected components. So up to an isotopy, you can just choose a basis. That's the same as choosing an orientation. Okay, but I think this example here is more interesting. Because in this example, what happens is that you have to choose, sort of, the framing has to switch, because when you get to this point, then sort of you have to, so the orientation induced here and the framing induced here and the framing induced here are opposite. But that's because you're changing the orientation of your point. So, you know, when you have a negative point, you don't take the framing that's induced from x, you take the opposite framing. Okay, that's kind of the natural framing. Okay, that's kind of what I meant by when I defined the framing induced from the orientation. So if you are at a positive point, that's exactly the framing on a positive basis of x. And if you're at a negative point, that's like the opposite of a basis on x. So it's a non-oriented basis. Okay, is that clear? I mean, if you want to, I can actually explain how, maybe I should do that, because I'm trying to do, how to get a framing on this part here that, you know, is induced from the framing on x. So what you do here, so for this loop here, this construction here won't work if you just do v, because the problem is that the tangent space is no longer going to be generated by ddt plus the tangent vector, because now sort of at some point ddt is gonna be 0. So remember what this eta tilde was. Eta tilde was this function that actually where the derivative is not identically 1, and then eta of t. So this, let me call this, I don't know, h of t. So now the tangent space along a point here is going to be generated by h prime of t times d dt plus eta prime of t. Oh, to be precise, this is at a point t eta of t. Oh, it's not really that. Let me just write eta tilde of t. Okay. So that's what it is. So this is, if I take an eta tilde here. And then now I have to be, kind of a little clever to find a natural isomorphism of the normal bundle. Now what I want to do is I want to find an isomorphism between the normal bundle of W and the tangent space to X at this point. At the point, no, not eta tilde, at the point eta of t. So remember, eta is just a path connecting 2 points. And one, has the positive orientation, and one had the negative orientation. So how do you find such an isomorphism? I mean, of course they are isomorphic because they have the same dimension. But what I'm claiming is that there is a natural isomorphism that is somehow kind of induced by this curve, eta tilde. So how do you do that? So actually, I'm going to see this tangent space as as generated by eta prime plus eta prime of t perp. Okay. And actually, I forgot to say one more condition on eta, which maybe is clear from the picture, but maybe I should have emphasized, which is that I want these to be locally constant. I mean, I want them to be constant near 0, near 1, but then I want the derivative to be different from 0 in most places. So, I want gamma prime to be different from 0 for t in, I don't know, 2 epsilon, 1 minus 2 epsilon, something like that. And the same thing for eta tilde. Especially for eta prime. I guess I don't really care that much about gamma because t is derivative is 1, but for eta I really need to make sure that the derivative of eta is different from 0 near 1/2. But I might as well assume that for 2 epsilon, 1 minus 2 epsilon. Okay, so putting this extra assumption, now unless I'm very close to 0, like unless I'm between 0 and epsilon, this doesn't quite work, but then the other thing will work. But if I'm away from 0, then I can actually write my tangent space of X. I can break it down into R times eta prime plus the orthogonal complement to eta prime. Okay, and then now I can take B times eta prime plus V. I can take that to the vector minus B ddt plus H prime of t times eta prime. And then plus V. I think that's what I do. And then you can check that this guy is indeed in the normal bundle. So this guy, when you take the inner product with this, let's see if this works. This is going to be
Can I ask a question?
yes.
W isn't the one manifold.
Yeah.
So how can the tangent space, the normal space is isomorphic to it? Sorry.
Yeah. So what I'm trying to do is I'm just trying to write down what's happening, as you take this, as you take the normal bundle, the normal space, and you move it around this eta, this image of this curve.
Okay. I got a little lost in what you're trying to do.
Okay.
You're trying to define like a normal space along the lines.
I mean, I have a normal space along the lines. I'm trying to define a framing, so I'm trying to fix a basis on each of these normal spaces.
That locally is trivial.
What do you mean locally trivial?
Like that you see it locally as a product. Is that what you want?
No, I just want to fix a basis there.
Okay.
Yeah. So if I know that if I have a canonical isomorphism with the tangent space to X, then at X, I know that I can fix a basis for every point. I can choose a prescribed one that, comes from the orientation, for example.
Okay. Thank you.
Yeah, you're welcome. Yeah, that is positive with respect to the orientation. So that's what I'm trying to do. So what I'm saying is because this thing loops around and this H prime is sometimes 0, that you won't, in general, be able to just do the same construction as before. Have this just inject the tangent space of X into here and then put something to compensate on DDT.
Okay.
That you see what I'm saying?
Yes, in the other curve it's simpler because you can make the derivative not 0.
Yeah, exactly. But here, because the H prime can be 0 sometimes, I think I did this right before the class, but I think this works. Let's see. First of all, we have to just, this is clearly injective, and you have to just see that it will be in the kernel. So this times this is minus b. Oh no, I think I need a b here too. Yeah. Sorry. Plus b eta prime of t, h prime of t, eta prime. I might have to divide by the norm of eta prime. Squared. Okay, I think now that's right. Okay, I think that's right. Sorry. But anyway, it doesn't matter exactly what the expression is. I think you can all figure this out. The point is that you have this picture right here. And the interesting thing is, if you look at this picture, what is happening here is that H prime is changing sign, like it's going from positive to negative. Is going from positive to negative. So when you project this to the tangent space of X at eta of t, unless t is 1/2, t 1/2 is when this is 0. But if t is not 1/2, you actually can project, and this is going to be an isomorphism, which is like what you get by just like eliminating this part. But you see that what you're doing is you're actually switching the orientation, because here you fix your orientation as you move along, and then when you go here, like first you're switching. if H prime is positive, then you have the same eta prime. And then if H prime is negative, then you switch the sign of eta prime without switching it here. So, I mean, this is kind of representing the fact, if you have your plane like this and you go along this curve, when you get to the other side, then the orientation is go the other way. It's going to go the other way. Okay? So that's consistent with the fact that one point comes with a plus and the other point comes with a minus. Okay, so if you choose the framings induced by the orientation of the points, then this cobordism is going to preserve the framings. That's what I'm trying to say. So in other words, the conclusion of this is just one example. The conclusion is if you have Q0 and Q1 sets of oriented points in X, such that the number of points in Q0 equals the number of points in Q1 with signs, so the sign count, then Q0 and Q1 are framed coordinate. Assuming, of course, that X is connected.
Professor.
Sim.
Você definiu o framing como a base global do fibrado normal, certo?
Sim.
Só que aí você está tentando definir o framing usando o X. Só que o X ele pode não ter campos certinhos em cima das curvas.
Não, mas é em cima do ponto, né? O fibrado normal, ele é um fibrado sobre a subvariedade.
Certo.
Então, se eu pego um ponto, eu preciso simplesmente escolher uma base para o fibrado normal naquele ponto. Ou seja, eu preciso escolher uma base para o espaço tangente naquele ponto. Isso eu sempre posso fazer.
Certo, mas você precisa variar isso suavemente pela curva.
Sim, mas é exatamente isso que eu estou fazendo aqui. Eu fiz as coisas meio ao contrário. Talvez o exemplo não esteja... Maybe, the example I did it backwards. But what I'm saying is if I have a curve, then I can choose a framing along the curve that's going to give you a basis on both ends that coincide with the orientation.
Certo. Tá. Já entendi, ok.
Maybe I should do a second example, which will help clarify this. The second example is if you just have an isotopy of framing. So say that you have a fixed submanifold, and then I have an isotopy of framings. What does that mean? That means, that eta t is a family of framing. So this is V1 T up to V K T, and these, for each T, these are framings of Q. Okay, so for T going from 0 to 1. And I claim that Q with the framing eta 0 is framed coordinate to Q with the framing eta 1. And well, how do you do that? It's actually very simple. What you do is you look at the submanifold, that you look at 0, 1 times Q contained in 0, 1 times X. And then the normal bundle of W at, say, T times Q, this is isomorphic to the normal bundle of Q. This is like this is a horizontal cobordism. I don't know, something like this. So then I can pick a framing here, which is just given by eta t. So, you can think of eta of t dot, this is by definition eta t. So this is a framing on W that clearly restricts to eta 0 and eta 1. So what this is saying basically is that being framed cobordant is kind of a weaker notion than being having isotopic framings. So if you fix a manifold and you choose a framing, if you just change the framing by anisotropy, you get the same framed submanifold. Okay, sorry, the same frame cobordism class. So this second example is why I was being a little sloppy with choosing the framing on the point, because technically a framing at a point is a choice of bases. But I'm basically saying, well, you can just choose an orientation. And an orientation is the same as an isotopic class of framings of a point at a point. Okay, so one more time, a framing at a point is just a choice of bases of the normal bundle, which is the same as a tangent of the tangent space, which is the same, the normal space, which is the same as a tangent space. So a framing is a choice of bases, and an orientation is a choice of an isotopic class of bases. Ok?
Vinícius, pelo
Oi.
que eu entendi naquele primeiro caso, no exemplo primeiro, se você pegar o transporte paralelo, daria certo no primeiro caso, que vai de uma borda para outra, mas na volta não daria certo. Não sei se o transporte paralelo preserva a orientação.
O problema, né, é que quando você chega nesse ponto aqui do meio, o transporte paralelo vai preservar a orientação, sim. Mas se você chega nesse ponto aqui do meio, o problema é que agora o espaço tangente, ele não é mais... Assim, na verdade, nem aqui no meio ele não vai ser mais perpendicular, mas vai existir um isomorfismo. Não é? Mas o problema é que quando você chega aqui no meio, o espaço tangente, o espaço tangente AX, ele não é mais transversal à curva.
Tá.
Tá?
Então, daria problema nesse caso, no outro caso não daria, que passa direto.
Na verdade, não. O transporte paralelo do espaço tangente, ele... Deixa eu ver aqui. Não, porque assim, eu acho que o transporte paralelo do espaço normal, ele não vai continuar, ele não vai ser sempre normal, a curva, esse que é o problema. Não é?
Devia preservar o produto interno, não? Mas a curva muda, né? Sim, a curva muda o vetor. Sim, entendi.
Tá. Okay. So I want to give one more example because I think it's kind of cool, which is the Hopf vibration. I guess maybe it's the first non-trivial or example that's a little bit more interesting. I think many of you have seen the Hopf vibration, maybe some have not. But this is the most famous map from S3 to S2. So what is this map? So if you think of S3 as the unit sphere in R4, which is the same as C2, you can consider the map that takes, say, Z1 and Z2 to CP1. So Z1, 2 dots Z2. Okay, so this and CP1 is the same as S2. This is the Hopf vibration. This is the easiest way to define it. But you could, if you're not so familiar with projective spaces, maybe this is a little intriguing to you. You can just think of it as, the map that goes from C2, from S3, contained in C2, to C union at point at infinity, where you just look at Z1, Z2, and you take it to the quotient of Z1 by Z2. z1 over z2. Okay, and the convention is that if z2 is 0, then you take this point to infinity. Okay, so this is the Hopf vibration, and an exercise is that all values are regular and then you could take the pre-image and all the pre-images, so all values, so let me write it like this. All y in S2, every is regular, and the pre-image of y is going to be a circle. Well, the fact that it's a circle isn't surprising because you know it has to be, if all the points are regular, and the pre-image has to be a submanifold, and it has to have dimension 1, and it has to be compact with no boundary. So it has to be a circle, unless it's disconnected. So it could be a disjoint union of circles. But it's but you can actually figure out exactly what it is. So because if you just take z1, z2, and you fix that to be equal to some point, z0, say, the only freedom that you have is to multiply z1 and z2 by a number of a complex number. So you have to, this, well, let's say z1 over z2 is equal to z0, and it's equal to, oh, sorry, y. And this is equal to z1 tilde over z2 tilde. So this is going to be if and only if z1, z2 is equal to lambda times z1 tilde, z2 tilde. And because these have to be have to have norm 1 in C2, then the norm of lambda has to be equal to 1. So this is the reason why. So, you know, basically lambda is in S1. This is the reason why the pre-image of y is isomorphic, or it's diffeomorphic to S1. Okay, so given 2 points in the pre-image of y, they have to differ by multiplying by lambda. Okay, so now it's maybe I should say, you know, the other thing that's kind of cool to see is what happens. Maybe you want to remove a point at infinity in S3. You can write S3 as R3 union the point at infinity, you know, using the stereographic projection, for example. And now you can write the Hopf vibration using the stereographic projection. And then you conclude that you can, maybe an exercise, more exercises, is to write the restriction of f to R3. And then you can do some calculations, and you can actually realize that the pre-image of 0 under this restriction, I mean, it's just going to be, you can think of it as being a unit circle. And a framing on this, so how do you look at a framing? As I told you last time, you can think of a frame as just being determined by one vector field. And so basically, you know, you just have to look at the tangent space of R2, which is just R2, and you, for example, you pick the Euclidean, one element of the Euclidean basis. You fix your E1, and you look at the pre-image of E1 by the map, and that's going to give you some vector field along here. But that's the same thing as actually, instead of taking the pre-image of 0, you can take the pre-image of a very nearby point. So say you take the pre-image of epsilon times E1. That's going to give you another knot And the exercise is to kind of compute which knot it is. So it's going to be another knot, and actually it's going to have linking number 1. So in some way, that's why this hop vibration is, it's kind of the generator of this. And as we'll see basically is that if you look at the homotopy classes of maps from S3 to S2, that's basically the same as all the possible framings here. So this is a very well-known result, is that this is isomorphic to Z. And this is also known as pi3 of S2. Okay, so that's kind of a digression. But are there any questions about what I said?
Vamos ver alguma coisa sobre número, link number?
Falar alguma coisa sobre linking number? Sim. Se você tem dois... okay, so what's the linking number? If you have two knots, or actually links in S3, let's start with knots. And they don't intersect. Then you have what's called the linking number. And you can compute the linking number in two different ways. I'll define it, you can define it in a topological way. And the definition is the following. You just look at Q as the boundary of some surface, sigma. So every knot in S3 is the boundary of some surface. So this sigma is called the Seifert surface. You can think about it, you can actually construct this explicitly, or you can just use some homological argument, because S3 doesn't have first homology, so everything has to be the boundary of something. You just have to prove this something is a smooth surface. And then the linking number is just the intersection number between sigma and L. So that's one definition. So here, you kind of consider this surface here, and then this other link, it intersects the surface exactly at one point. Okay, so the linking number is 1 or minus 1. You have to orient things to make this, to define a sign. But another way you can actually just look at knot projections and compute this intersection number without ever talking about the surface. So if you have knots, I don't know, say you have a situation like this, and this is K and this is L, you can compute the linking number by just looking at the projection. So when I draw these two knots, I'm actually thinking of the two projections. So I can see the places where the two projections intersect. So here's one, here's another one, here's another one, here's another one. So this is where the projections to R2 intersect. And then I just count the number of intersections of the projection of K to R2 and the projection of L to R2. But they could intersect in different ways, or they could, I have to look at the orientation of the knots and which one goes above. So if you have a crossing like this, then this counts as a plus. And if you have a crossing like this, then this counts as a minus. And you can prove that this definition coincides with this definition if you orient things correctly. Okay? So,
okay, thanks, nice.
You're welcome. This is just a little introduction, but you can think about this more. But now I want to talk about the Pontryagin Thom construction. So let's recall that if you have a function, now I have a function from x to Sm, and x has dimension n, and I'm assuming n is bigger than or equal to m. Okay, and I'm also assuming that x is compact, oriented, without boundary. Okay, so now I take a regular value. Say I take a regular value of f. And then what I said last time is that the preimage of A is a framed submanifold. And why is that? Well, we know it's a submanifold by I guess the implicit function theorem. And the framing just comes from the fact that, you know, at every point in the preimage, so if I call this Q, so for every x in Q, the derivative is an isomorphism on the normal bundle. So this takes the normal bundle of Q to the tangent space at A of Sm, and this is an isomorphism. So I can fix an oriented basis of the tangent space to Sm, and I can consider the preimage, and that will give me a framing of the normal bundle, a framing of Q. And again, this framing is not completely canonical because it depends on which choice of bases I have. But as I showed you a little before, any oriented basis is going to be isotopic to any other oriented basis. So all these framings are going to be equivalent up to frame cobordisms. Okay, but even more. So if I take two different regular values, so if A and B are different regular values of f, then I claim that the preimage of A with this given framing is framed cobordant to the preimage of B. Okay. So we've already seen that it doesn't really matter which oriented basis I choose for A. So you know, I basically can choose whichever one I want. I'm going to have the same framing up to framed cobordism. But the point now is that I can also choose a different regular value. And why is that? Let's see how we get this framed cobordism. Well, if I can consider a map from, yeah, so yeah, basically I can have a homotopy of maps from x to Sm such that f0 is equal to f, and such that f1, the preimage of f1 of B, is equal to the preimage like that. Okay, so what I can do is I can homotope my my function so that the preimage of this, oh, sorry, I actually wanted A switched with B. Yeah, so this is what I do. Okay, so, and because we have a homotopy, then as I'll show you, this guy is now going to be framed cobordant to the preimage of A. Okay, so let me write the argument. So first of all, if I have 2 points in Sn, then I can find a path that goes from one to the other. I can actually find a family of, I can find the flow of a vector field that goes from Sm to Sm. such that phi1 of A is equal to B. I mean, there are lots of ways to do that, but I can, for example, choose a rotation along some geodesic, or, you can just pick any, like, it's kind of simple to find a vector field that does that, whose time one flow will take A to B. Okay, and this, of course, this is oriented because this is isotopic to the identity, which is phi 0. Okay, so now you can define Ft to be phi t composed with F. Okay, so that now, this is going to be a map from X to Sm, and then phi t of phi 0, F0 is equal to F, and F1, the pre-image of A is going to be sorry, I want F1 to take B to A. Yeah, B to A. So this is going to be the pre-image of phi1 inverse of A, which is the pre-image of B. So now, I have a homotopy, and I know that, and I want to prove that I want to look at the pre-image of A, and I want to look at the pre-image of A by F1. I think I already did this last time, but I claim that these two are frame coordinate. So to do that, I have to maybe first, I have to perturb Ft slightly so that A is still a regular value for the homotopy, so that Ft is still transverse to A. I might have to do that. And then if I do that, then I can look at the function that goes from x, from 0, 1 times x to Sn, and this is kind of Sm. Now this is a very standard argument that just takes x and t to Ft of x. And then because the homotopy is transverse to A, then I can take the pre-image of A, and this is going to be a manifold, compact manifold with boundary given by F1 inverse of A minus F0 inverse of A. Okay, so this is the cobordism. And then clearly, I mean, I can just, because it's a cobordism defined this way, then I also get a framing by just taking the pre-image of a given basis of the tangent space of Sm at A. Okay, so this argument, I'm showing two things. I'm showing that for a given function, I mean, I kind of did two proofs at the same. What I did is for a given function, the pre-image of A is frame cobordant to the pre-image of B. And I also showed that if I have two homotopic functions, then the pre-image of A is frame cobordant to the pre-image of A by G. Okay, so now maybe the theorem, the statement of the theorem will be clear. So actually before that, let me just say that this fact here is what we need to say that given a function from X to Sm, we have a manifold that's called the Pontryagin manifold. So first of all, let me just say that. So given a function we obtain this pre-image of a regular value with the framing is called the Pontryagin manifold. And this is well defined up to a framed cobordism. So maybe it's more, it's clear to think about this as like there's a framed cobordism class of manifolds, of submanifolds of X. So given a function, I have this framed cobordism class. And the second fact here is that if you homotope your function, you get the same framed cobordism class. So what this is saying is that if I look at the homotopy classes of X to Sm, and this goes to the set of framed submanifolds of X quotiented by framed cobordisms. So we have a map, capital Phi, that takes a function to the pre-image of a regular value. Okay, so these two facts here mean that this map, capital Phi, is well defined. So if I have a function, I can just take the pre-image of any regular value and I have the same submanifold up to framed cobordism. And if I take a homotopic function, I also have the same framed submanifold up to framed cobordism. Okay, is this clear? This is what's called the Pontryagin-Thom construction. And the theorem is that Phi is a bijection. Oh, yeah.
Professor, se você pegar só cobordismos orientados, eles classificam alguma coisa?
Boa pergunta. Eu acho que não.
Parece que os dois são, sei lá, estruturas, reduções da estrutura do estrutura da variedade. Eu não sei se...
Eu acho que só cobordismos orientados, não, em geral, não classificam nada.
Certo.
Não sei, é uma pergunta mais sutil de topologia algébrica, de teoria da homotopia. Eu acho que se você pegar... É porque isso, na verdade, é uma área de pesquisa, cobordismos e tal. Se você tiver no caso não orientado, aí você pode pensar em subvariedades módulo cobordismos, sem framings, né? Bom, eu não sei. Você vai ter um mapa em uma direção, né? Você pode simplesmente esquecer os framings. E aí você vai ter um mapa em uma direção. Agora, isso não vai ser um mapa injetivo. Em geral, acho que esse é o problema. Você pode ir daqui para as subvariedades orientadas, oriented submanifolds, where you just forget the framing. And then modulo cobordism, oriented cobordisms. Sorry, this is not surjective because you could maybe have oriented submanifolds that are not framed. Yeah, so you could have a map like this, but I don't know how to say that this map is either not even surjective and even less injective. So, yeah, I don't know if there's another thing another quotient you can put to have an injective or surjective map. But anyway, let's prove this theorem. And if you understood the proof of the Hopf degree theorem last time, then maybe you should be able to construct the proof here. But anyway, for completion, let me do it again. Basically, it's going to be very similar, but maybe if you haven't understood last time, we can understand better here. And we generalized the statement, but the proof is basically the same. Okay, so first of all, let's see that this map phi is surjective. So in other words, I can, given a framed submanifold, I can always attain it as a pre-image of a regular value of a map from X to Sm. So say that we have Q, eta. This is a framed submanifold of X. And I first claim that we can obtain this framed submanifold as the pre-image. The claim is that this guy can be obtained as the pre-image of A for some F going from X to Sm. Okay, so the construction is actually quite simple. So what you do is you use the framing. So what's the framing? The framing will give rise to an isomorphism of the normal bundle with Q times Rk. Say that K is the codimension of Q. Oh, sorry. It has to be, so they have to be m-dimensional, obviously. So it's actually the same as m. Because the pre-image of a regular value is going to have the same codimension, m codimensional submanifolds. Yeah, so it has to be Rm. Okay, and then we can use, sort of the exponential map or something to define. Once we have this, then we can define, as I said last time, an embedding of Q times Rm into your manifold X. Okay, so for example, using the exponential map. So you can, if you have your Q, then you can look at a neighborhood of Q, and the framing actually gives you a diffeomorphism of a neighborhood of Q with Q times Rm. Okay, so now it's very simple. I define f of, like say the coordinates here are x and u. I just define f of p to be u if, no. Yeah, so let me be more clear. So in this neighborhood, I just define the function to be, I define a function on Rm that's just the second coordinate. So I take this to be the projection to the second coordinate, so taking xu to u. And then I look at Rm inside of Sm. So this is Sm minus some point, I don't know which point you want. You remove some minus a. So this takes 0 to a. Okay, so now if you, on the, in the cylinder here, in this tubular neighborhood, you define the function just like that. So this is, if you want, this is the inverse of the stereographic projection. So it's psi inverse. So you define f of p to be psi inverse of u if p is phi of xu, and you define it to be minus a otherwise. So, so kind of for each slice here, for each kind of slice corresponding to the normal bundle, you map this this whole Rm to the sphere minus a point, and then this whole boundary is being mapped to minus a, and then outside this, you map everything to minus a. So you can check that the pre-image of A is going to be exactly equal to Q. And that the framing corresponds to eta. Okay, because the framing is the same, you know, is the framing coming from Rm. Okay. Any questions? We did something very similar last time, twice. But if you don't understand something, please say it. So we proved this is surjective. Now we need to prove that it's injective. So we have to prove that if two functions have the same frame cobordism, if they have the same submanifold up to frame cobordism, then they have to be homotopic. And you could assume that the regular values is the same. So what I'm going to do is, suppose f and g are functions from x to Sm, such that the pre-image of A is framed cobordant to the pre-image of A, G inverse of A, then F is homotopic to G. Okay, so it's going to be very similar to last time. So if they're framed cobordant, then we can say that, so this is the claim. So now the proof of the claim. So let W in 0, 1 times x be the framed cobordism between the preimage of A and the preimage of A by G. So then the first step will be define a homotopy H from 0, 1 times x to Sm. Not between F and G, but just a homotopy. And it's going to be between F tilde and G tilde. And the way they define a homotopy is basically you look at this framed cobordism and then you apply this construction here, the same construction, to just define a map onto Sm. So like using W, we just define a map, which is the map H, such that the pre-image of A is just equal to W. Okay, so it's exactly the same thing here. You look at a tubular neighborhood of W. So W is framed. So a neighborhood of W is diffeomorphic to W times R to the M. Okay, so how do you do that? So since W is framed, we can find an embedding. We can embed W times Rm into 0, 1 times x. Okay, and this embedding is given by the framing, the identification with Rm. Okay, and then now you just do the same thing. Like on Rm, you just take the identity, and then you take the inverse of the stereographic projection, And then outside of this tubular neighborhood, you just define it to be the identity function. But the point is, so then you define this function on this 0, 1 times x into Sm, and if you just take f tilde to be h of 0 dot, and g tilde to be h of 1 dot, I mean, of course they are homotopic, but what's interesting, is because of how this is defined explicitly, that when you look at the boundary of the map H, that's going to be the preimage of A is going to be the same as F and as G, because W was the frame coordinate between these two. So the point is that if you look at the boundary of H inverse of A, so this is the boundary of W, this is equal to the restriction of H to the boundary inverse of A. So yeah. Okay. So now, basically we have this F, we have the F tilde, we have the G tilde, and we have the G. And we know that these two have the same preimage at A. The preimage at A is the same, and these two have the same preimage at A. And here we know that these two are homotopic. So what we need to show now is that these two are homotopic and that these two are homotopic. Okay, so now the second step is, so suppose that F and F tilde are maps from X to Sm such that the preimage of A is the same as framed submanifolds. So they are the same submanifold and the framings coincide. Then we want to prove that they are homotopic. And again, just like last time, we have to do two things. We first homotope them near this Q, and then you homotope it away from Q. So let's call this Q. So then you homotope it near Q, and then you homotope it away from Q. Okay. And here's the thing, basically, because they're the same framed submanifolds, you can write it like this: Q times. So near Q, you just have a neighborhood of Q is just Q times Rm. And here's the detail that maybe I should emphasize, is that because these are framed, then you can actually suppose that and A is a regular value. You can, by the implicit function theorem, by the implicit function theorem, you can suppose. Well, actually, you don't even need the implicit function theorem for this. You can just, because of the way they define the framing, you can suppose, for example, that df at x dot is the identity at least for u equals 0. I mean, I think you can even just assume this is the projection if you find smart enough embedding. Yeah, so I think I think if you actually really do things right, you can find another chart so that this is actually the projection onto the second coordinate. But if you don't quite assume it's a projection, just because this embedding is defined with the framing, you can at least assume that df so if this is x and u, and this is your f, when you look at df du, this is going to go from Rm to Rm, that the derivative, that this at 0 has positive determinant. I mean, that's kind of all you need to assume. But if you're a little clever, if you start using the inverse function theorem, you can assume that it's the projection, or at least this is the identity. You can do different things if you're willing to change the chart here. But if you just want to take your given stereographic projection, then maybe you just assume this determinant is positive. Okay. And then that's what you kind of need to say, what I'd written last time is that f of xu dotted with u is bigger than 0 for u sufficiently small, but also different from 0. This is the condition that you need to be able to interpolate from f to f tilde and say that you don't get any new zeros. Okay, so let me now write this down. Like why can you prove that? How do you know this? Well, you know that f of xu is equal to say some. If you just suppose this is the identity, for example, I think that's enough at 0, then this is going to be u plus some u o of norm of u squared. I think you could, you could put a matrix here if you want, but whatever, let me just do the easiest possible calculation. So then you have that this minus u is less than or equal to some constant times norm of u squared. So when you take the inner product with u, you look at the absolute value, that's less than or equal to c u cubed, so that now you can open this up, and f of xu dotted with u is bigger than or equal to norm of u squared minus c norm of u cubed. And now you see that if u is sufficiently small, then this guy is positive, as long as u is different from 0. Okay, but it's essential to have this condition here that the f du is the identity, or it's at least positive definite, a positive matrix. Okay. So anyway, you can figure out the details if there's still some missing holes for you. But then the idea is now you just interpolate with a t from one to the other to f tilde. But you really want to pick a bump function, because you want not to interpolate outside of a neighborhood, because then you could be introducing new zeros. So you actually put a bump function here. And this bump function is 1 in the ball of radius epsilon over 2, and the support is contained in the ball of radius epsilon. So then you do this homotopy, and then outside of this ball, then you can do another homotopy using the other stereographic projection. Okay, so outside this neighborhood, we can do another homotopy using the other stereographic projection. Okay, so it's a little subtle, but it's just this. And answering the question that someone asked last time about trying to do this for just points when the orientations aren't what you need, like they don't come with just matching points without taking care of the orientation, you have exactly this problem here, that you won't be able to show, you won't have that this projection, that this the function is given by the projection or something positive, and which is what you need for this positivity condition, which is what you need to just make sure that this homotopy will not have any new zeros. Okay. And yeah, to see, if you had created a new zero here, then when you took the inner product with u, then if these guys are not zero, if you're away from the zero, then these two would be strictly positive, and then this thing would be strictly positive. Okay. Sorry, I think the row, it goes next to t, not next to this. Yeah, there we go. Okay, so I think that's the end of the proof of the Pontryagin-Thom construction. Yeah, I encourage you, if you got a little lost, I encourage you to try to redo this proof on your own. And if you need help, you can go to Milner's book. And just also try to redo the proof of Hopf's theorem, which is exactly this, but in the case where the dimension of x is equal to m. Okay, so let's finish here.